Hello guys, this is 9.4. We just have a few more sections to go. 9.7 and 9.8 are optional, so depending on the time, I don't think we will be able to get to 9.7 and 9.8, but my goal is to get to 9.4 through 9.6. All right, so this is 9.4, linear systems in normal form. So have your notes open up next to you. And we're going to start by talking about what a normal form is. Okay, so a normal form is a differential equation in this form, right? X prime of t minus a of t, x of t is equal to some function f of t. Now in here, the x of t that we're looking at is a vector of small functions x1 of t up to xn of t. Okay? All right, so it's a vector of functions, and f of t is another vector of functions that is f1 of t up to fn of t, right? Just some another vector of functions, right? And the matrix A of t is similar to the matrix that we saw in 9.3, right? It's just a matrix that is n by n, right? N by n. And then we have all the entries, right? A11 of t up to A1n of t, and then an1 of t up to ann of t. Right? So each of these entries is some function. Right? And furthermore, we say that this system is homogeneous if f of t is equal to 0. Right? It's homogeneous if you get I don't know why I have the little dot there. All right, so homogeneous is when f of t is equal to 0, meaning you get a vector of 0, like this. Right, for all the small function f, right, f1 up to fn, if they're all zeros, then we say that the system is homogeneous, else it's non-homogeneous. Okay, so if one of the little function f1 up to fn, if one of them is not a 0, then we say that the system is non-homogeneous. All right, next let's take a look at the notes starting from here. Right, so an nth order linear differential equation that is in this form. Right, so we have y to the nth derivative plus pn minus 1 t y to the n minus 1 derivative up to down to p naught times y of t is equal to g of t. Now this is an nth order linear differential equation, right? Nth order, and through substitution, we can rewrite that as a system of first order, which is here. This is a substitution. So let x1 be equal to y of t, x2 be y prime of t, up to xn be y of the n minus 1 derivative of t. So equation 2 is equivalent to this normal form right here. Okay, so later on we'll show you guys with an example of how we can do this. So it's okay if it's a little confusing for now. Later on, you can pause the video, read over this section, and towards the end of the video, we will do some examples together. All right, next let's look at theorem 2, existence and uniqueness. If a of t and f of t are continuous on an open interval I that contains the point t naught, then any choice of the initial vector x naught, there exists a unique solution x of t on the whole interval to the initial value problem, the normal form right here with some initial condition. And we may write the system as x prime minus ax is equal to f. Let L be x minus ax, and L is the linear operator. So basically what theorem 2 is saying is there is going to, if they're continuous on an open interval I that contains the initial condition, then we can find a solution to the initial value problem. Theorem 2 is basically tells that we can actually solve the system and we can find a solution. Now the proof is actually quite complicated, and if you're interested, I think the proof can be found in chapter 13 in the textbook. All right, next definition one. The n-vector function x1 to xm are linearly dependent on an open interval I. Then there exists constant c1 to cm, not all zero, such that the linear combination of x1 to xm with the constant c's is equal to 0. Right? So this is similar to the definition that we saw in linear algebra as linear independence versus linear dependence. Right? So if you can find at least one combination of C1 to Cm that not all of them are 0, then we say that the system is linearly dependent, right? So the same idea. All right, next definition, the Wronskian of n vectors, right? So now we have n vectors, x1 up to xn, and each one of them consists of vector of little functions, right? So all the x1, 1, 1, 2, x1, 1, 2, 1 up to n1, these are all some function. And also xn, x1n up to xnn, they are all just some function, right? And then the Wronskian here, we're defining as the matrix, the determinant of the matrix when you put all the x1 and xn in the form of a matrix, right? So the Wronskian here is a little different than the ones that we saw in 9.1. In 9.1, we are looking at the first row is the function, and then second row is the first derivative, second derivative, and so on. But here we are looking at each column has different types of function, and then the Wronskian is just the determinant of that. All right, next let's look at this remark and proposition. So these two items are very similar to one of the theorems we saw in 9.1. So let's just do a quick review on this. All right, let's look at the remark first. Vector functions x1 to xn are linearly independent. Now remember that x1 to xn, they are a vector. They are all vectors with little functions in them. So they are linearly independent on the interval if their Wronskian is non-zero at any point in the interval, right? So let's scroll up a little bit, right? Remember the Wronskian is the determinant of this matrix, right? So if you can show that the Wronskian is non-zero, then we can say that they are linearly independent. Vice versa, if the Wronskian is 0, then that means they are linearly dependent, right? So let's look at the proposition. If vector functions x1 to xn are independent solutions to a homogeneous system, Lx equal to 0, that is, x prime minus ax is equal to 0, right? That's the homogeneous case because our function f, remember the normal form, f is a 0 vector, then the Wronskian is never 0 on I. Right? So if they are independent, then the Wronskian is never 0. Right? So if you want to take a look at the proof, it's down here, but we're not going to focus on that for now. I know this is can be a little confusing because we're seeing a lot of theoretical stuff, but don't worry. Later on, we will look at many different examples together. All right, so next we have two corollaries. Let's look at them together. They're basically saying the same thing, right? So let's look at the first one. The Wronskian of the solution x prime equal to ax, right? This is the same thing as this one, right? The homogeneous case. X prime minus ax is equal to 0 is the same thing as saying x prime is equal to ax. Is either identically 0 or never 0 on I. Okay, so meaning they are either, if it's never 0, that means they are linearly independent. If it's identically 0, that means they are linearly dependent. Right, so let's look at the second corollary. A set of n solutions, x1 to xn, to the homogeneous case, is linearly independent on I if and only if their Wronskian is never 0 on I. Right? So here we can see that again, having the condition Wronskian is never 0 is tied to linearly independence. Okay, let me say that again. You have linearly independence if the Wronskian is never 0. Okay, and we will see that in a second with an example. All right, next, theorem 3. Theorem 3 is just telling us how we can write solutions for homogeneous case, right? Homogeneous case having 0 on the right-hand side. So this is similar to our system of equation, right? The homogeneous case is just the linear combination of all the independent solutions, right? So x1 to xn are linearly independent solutions. Then the journal solution is just a linear combination of x1 to xn with some constant c1 to cn. Right? So instead of having just functions, here we have a vector of functions, right? So it's kind of like the same idea as in the first order linear differential equation. All right, so in theorem 3, we looked at the homogeneous case. Theorem 4 tells us about the non-homogeneous case, right? So now that our f of t is not 0 anymore, it's going to be some function. The general solution can be expressed as this part, equation 7, right? So you have c1x1 up to cnxn. Now, that looks familiar, right? That is the homogeneous case, right? The solution to the homogeneous case with the particular solution, right? So xp is a particular solution to the non-homogeneous system. You just add that at the end of the homogeneous solution. And again, this is very similar to our non-homogeneous first and second order linear differential equation. Okay. Next, we are going to look at how we can actually solve the systems, right? And then after that, we will look at a bunch of examples together. All right, so 9.4.1, this shows us, give us an overview on how to solve normal systems, both homogeneous case and non-homogeneous case. Now, this again is very confusing because we are not actually working with any numbers. So if you want, you can take a look at this, but we're going to come back to this in more details when we are actually working with a actual system with an example. Okay, so without further ado, let's look at some of the examples we have. Okay, so let's start with example 1. Write the given system in the matrix form x prime minus ax is equal to f. And that's the system we have right here. All right, so let's look at this system together. Right, we have dx dt, dy dt, dz dt. Right, so on the left-hand side, we can say that on the left-hand side, we just have all the derivatives, right? So we say that x prime, y prime, and z prime, right? So x, y, and z are our three functions that we are looking at. So left-hand side, x prime, right? This x prime, we can write that as x, y, z prime, right? Like this. All right, so next we need to figure out ax, right? So this part right here, that's going to give us our ax and possibly f, right? If we move the minus ax on the right, we can rewrite this as x prime is equal to ax plus f, right? So we have the x prime on the left-hand side. That means on the right-hand side, we should have ax plus f instead of minus ax is equal to f. All right, so let's rewrite this. I missed a z here. There's a z here. All right, next, let's look at this thing, right? So notice that all the terms in here they either have x, y, or z. That means I can actually rewrite this as a matrix multiplied by x, y, z. All right, let's look at the first equation, first row, right? X plus y plus z. So that means we have 1, 1, and 1. And the second one, we have 2x minus y plus 3z. That means it's 2, negative 1, and 3. The third one, x plus 5z. So that's x is 1, and y is 0, and z is 5. Now notice how we have used everything here. So what can we say about f, right? What is, if we have covered everything, then what is f going to be? Right? We don't see f, so in this case, f is equal to the 0 vector, right? So we get 3 zeros like that. Okay. All right. Now we can put everything in this form. So x prime minus ax is equal to f, right? So we have x prime, which is this, right? So we have x, y, z prime minus a is this matrix right here, right? This is a 1, 1, 1, 2, negative 1, 3, 1, 0, 5 times x, which is the vector x, which is x, y, z, right, is equal to f. And f is 0, 0, 0, like that. Okay. So this is how you can convert a system of a differential equation. Now, how to rewrite using these three differential equations and writing it as a system or a matrix form. Okay, next we are looking at example 2. Rewrite the scalar equation as a first order system in normal form. Express the system in the matrix form x prime minus ax is equal to f. Okay, so this is our third order linear differential equation. Okay, and let's see how we can convert that into a system. Right. So first, you're gonna notice that this is actually non-homogeneous, right? We have some function cosine t, in fact, on the right hand side, and let's see if when we convert to the system, is it going to be homogeneous or non-homogeneous? Okay. So the technique we are going to use is we're going to introduce a bunch of xi's, right, to substitute for all the y primes. It's in the notes earlier. Let me show you in a second. Okay, so we saw this earlier in the video. An nth order linear differential equation, right, that's in this form, can be written as a first order system in normal form using substitution, right? So let x1 be y, x2 be y prime, x3 be double prime, and so on, right? So let's see that how that works in the actual example. All right, so let's look at this. We have a third order linear differential equation. So it's a third order. That means we need to introduce three variables, x1, x2, and x3. Okay, third order, so three of them. And to substitute them, it's very easy. You start with y, y prime, and then y double prime. Okay. So one question that you might ask is, okay, we have third order, that means it's y triple prime, but we only got to y double prime. Okay, so if that's a question you have, don't worry, because we are actually going to name x1, x2, x3. We're going to look at that as a vector and then call that x in general. Okay, so keep that in mind. When we introduce x1, x2, x3, we're going to put them in vector form, call that vector in general just x, right? So when we look at x prime, that means we're taking the derivative of x1 and x2 and x3. And when we take x3 prime, that means we're going to take take derivative of y double prime, which will give us y triple prime. Okay, so that is going to work out, trust me. Right? So if you have third order, then you will include, it will choose 3 more variables. If you have 4th order, then you will do 4 and so on, right? And anyway, at the end, you are going to have one less prime than, one less order in here than the original equation, differential equation. Okay, and let's move on and see how we can rewrite this differential equation in the system in a normal form. All right, so we have taken care of x prime, right? That's going to be just x1, x2, x3 prime. All right, and let's look at how we can get ax. Okay, so this part is a little trickier. All right, we have x prime minus ax equal to f. Right, so I'm going to ignore f for a second. Right, we don't know if it's a 0 or not, but assuming that's a 0, so we have a homogeneous case. Right, we have x prime minus ax is equal to 0. That means x prime is equal to ax. Right, okay. And let's write this out. So x prime is x1 prime, x2 prime, x3 prime, right, is equal to some matrix A multiplied by x1, x2, and x3. Okay. Now x1 prime is right here, right? x1, well, this is x1 is equal to y, so xy prime is actually equal to y prime, and we know y prime is x2. So that means for x1 prime, there is going to be an x2 in here, right? So x2 is going to be 1, and then the other 2 is going to be 0, right? Let me show you a little bit of what I'm doing here, right? So we know that x1 is equal to y. That means x1 prime is equal to y prime. Well, y prime is equal to x2, so x1 prime is actually equal to x2, right? So that means for x1 prime, there is going to be an x2 in there. And what about x2 prime? Right, let's look at x2 prime. Right, x2 is equal to y prime. That means x2 prime is equal to y double prime. And what is y double prime? Y double prime is x3, right? So x3, oops, no, sorry, x2 prime is equal to x3, right? So there's going to be an x3 and x2 prime. That means there's going to be a 1 here and 0, 0. Okay. Now I want you guys to look at this form, right? We have 1 going this way, and I'm going to show you in this, show you now in the notes, like the general form. All right, right here. So we have the matrix A. Notice that it's going to start with the second column in the first row, and then it's going to be 1 down to the bottom right, right? One off the diagonal is going to be all ones, and then the last row is going to be something else, right? So 1, 1, 1, 1 down here, which is very similar to what we have in our notes, right? We have 1 going this way, but since it's 3 by 3, we don't actually see that beautiful ones going down this way. Okay, and the last thing is, what about the last row, right? There are 2 ways you can do this. You can either just use the normal form, the notes, right here, negative p naught, negative p1, negative p2, and so on, right? All the p's, they are the coefficients of all the y's and all the y prime, y double prime, and so on here. Right? Right, so let's see. The first spot is going to be negative p0. So p0 is a coefficient of y. So y, the coefficient of y is 1. That means we're going to have a negative 1 here. Actually, let me use a different color. right? So the coefficient here is 1. That's P naught is 1. So we have -1 here, right? If you look at the normal form, it's actually has the opposite sign. Next is P1, negative P1. So here we have P1 is -1. So the opposite of -1 will be 1. And the last one will be negative P2. Now, we actually don't have a P2 here, right? Because we don't have the second derivative of y. So P2 will just be 0, right? And that will be your matrix A. Okay. All right. So we have taken care of the x prime and ax part. What about the f part, right? Because we assume that this is a 0, but then in fact it's actually not equal to 0 because we have this extra cosine t here. Okay, so how do we take care of that? Right, so excuse me. So let's say we have some function f here, right? So it's not 0 anymore, it's some function f, right? That means when I move the ax to the right hand side, it's gonna be plus f. Okay. So what is this f, right? We need to add some vector f, that's a function, on the right-hand side. And what goes in here, right? That's what we're trying to find out. All right, so let's go back to the notes again. All right, and if you look at this part, it actually tells you what f is, right? F is going to be the vector of all zeros, and the very last entry is going to be g of t. What is g of t? Right here, right? G of t is the function that makes the system, the differential equation non-homogeneous, right? So in our case, what is our g of t? All right, our g of t is this thing, right? The cosine of t, right? That means the f here, the vector f, we're gonna have 0, 0 for the first two entries, and the very last entry is going to be cosine t. Okay, and that whole thing is our vector function f. Okay, now notice that f is non-zero, right? Even though the first two entries are 0, but the last entry is non-zero. So we have ourselves a non-homogeneous case, right? We have x prime is equal to a times x plus f, right? Now, if you want to put it in the form of x prime minus ax equal to f, you simply move this product ax to the left hand side, and then we're done. Now, depending on the homework, they might ask you for x prime minus ax equal to f, or x prime equal to ax plus f, right? All it matters is where you put your ax, right? On the left hand side or on the right hand side. It actually doesn't matter, but be very careful of what the question is asking. Okay, so let's recap this example again, right? So we started with a third order linear differential equation. And in order to put this in normal form, in matrix form, we have to introduce new variables, x1, x2, and x3. Now, we pick 3 of them because we are looking at a third order, right? We pick 3 of them, x1, x2, and x3, because we're looking at third order differential equations. All right, and then what they are substituting is just basically y prime, y double prime, right? So increase the number of derivatives. All right, next, we want to put them in a matrix form, right? X prime equal to ax. So we started with x prime equal to ax. If you want, you can look at the general form from the notes, right? We have ones down this way. And then for the last row, we just look at the coefficient of y prime, y double prime, and so on, right? And make sure they are opposite of each other. And there is also another way to figure out all the entries in here, right? So for the first two, we saw it on the right hand side here, right? We actually derived to see what x1 prime and x2 prime are made of, right? And we saw that they are made of x2 and x3. Now you can actually do the same thing with x3 prime, right? So let me do a little side work here. X3 prime is equal to y triple prime. Okay. Now y triple prime is only found in here, right? So you can rewrite this as y triple prime minus y prime plus y, and then move everything to the right hand side, and that will tell you what y triple prime is made of. And you can just do substitution back using x1 and x2 to find what goes in here. Okay. And the last part, we have the plus f, which gives you the extra cosine t, and you will find the cosine t actually from here as well. When you move these two terms to the right hand side, you're gonna have one extra term, which is the cosine t, that does not belong in the matrix, right? So that's why we added at the end using the vector function f. Okay, so that's how you get the cosine t here. Okay. All right, cool. Feel free to let me know if you have any questions. Come to my office hour. Again, it's every Tuesday, Thursday from 1 to 3 p.m. The link is available on Blackboard. All right, so that's example 2. Let's look at our next example. All right, let's look at example 3, linearly independent, Li, or linearly dependent, LD, on a negative infinity to positive infinity, right? So part A, we have these two vector functions, right? And to check this, very easy. Let's just find the Wronskian, all right? And if we can show that they are non-zero, then they are linearly independent. Oops. Okay, there you go. All right, so multiply that way, subtract that way. All right, so we get t e to the negative 2t minus e to the negative 2t, like that. Right, and that's equal to e to the negative 2t, t minus 1. All right, so here we run into an issue because this is actually equal to 0 when t is equal to 1. Now, the theorem says if Wronskian is non-zero, then that means linearly independent, right? But here we actually have Wronskian is 0 at t equal to 1. So with this theorem, we can only say that if we show that this is non-zero everywhere, then it's linearly dependent. If it's 0 somewhere, we cannot say it's equal to linear dependence. So maybe it is 0 somewhere does not directly imply that it's linearly dependent, because this is not an if and only if theorem, right? If it's if and only if, then we can say that this brings us to linearly dependent, right? So in this case, using the Wronskian is inconclusive, so we just try another method, right? So C1 t e to the negative t, e to the negative t, plus C2 e to the negative t, e to the negative t, right? By definition, right, we want this to be 0, and we can show that it's linearly independent if C1 and C2 are both zeros, right? So for the second row, right, we can do an opposite then to make them 0. But for the first row, right, we have this extra t here, so there's no way we can make these two cancel each other without picking a value for t, right? Because we have this one extra t in the front, but not here, right? So from this view, C1 has to be equal to C2, which has to be 0. Then we can say that, yes, they are linearly independent. Right? But I just want to show you how Wronskian works, and sometimes we run into issues like this. Right? Wronskian is useful in this case when we are using vector functions, right? All the x's, and if we can show that this is always non-zero, then it's linearly independent. If it's 0 somewhere, then we have to use something else. All right, now this is actually a little different than the Wronskian that we saw in 6.1. Right, so make sure you know the difference. The one in 6.1, we're looking at the solutions to the differential equation. All right, so by using definition, we show that this is linearly independent. All right, let's move on to example 2. Sorry, not 2, 3b. Right, so we have 3 vector functions, right? Sine, cosine, sine, sine, cosine, cosine. I want to show that whether they are linearly independent or linearly dependent. All right, so since we have 3 of them and they are in each of them only has 2 entries, there is no way to use Wronskian, right? Because the dimension is not going to match up. So we're just going to use a definition. All right, sine t, cosine t, C2, sine t, and then plus C3, cosine t, cosine t. And we want them to be equal to 0. All right, so they are trig functions, and we are very familiar with trig functions. Now, let's just look at the first row, right? We have C1 sine t, C1 sine t plus C2 sine t plus C3 cosine t is equal to 0. All right, let's see. So if we want to make this true, let's say I pick C1 to be 1 and C2 to be -1, right? That way the first 2 terms will cancel, and we'll just make C3 0. So this also gives us 0, right? So that's one attempt that we can try, and let's see if it matches the second one. Right, so C1 cosine t plus C2 sine t. Now this is the second row, plus C3 cosine t. And if we plug in all the same C1, C2, and C3, we get what? Negative cosine t plus sine t plus 0, right? Which is not equal to 0. Right, so you can actually try many different combinations, but you can see that they are trig functions. So there's, if you want to cancel the second row, right, cancel the cosine, right, by picking 1 here and -1 and pick a 0 here, then we will still be left with a sine up here. I say there's no way that we can make this work by picking non-zero C1, C2, and C3. Right, so only case we have is C1 is equal to C2 is equal to C3, which is equal to 0, and that means they are linearly independent. Right, so something like this, we can just give that a try, and then of course if something's gonna work, then it's pretty easy to find them, because after all we have a lot of freedom on C1, C2, and C3. And as soon as you see that something is not going to work, then you can say that, okay, they must all be 0. All right, next let's look at our last example 4. All right, so example 4, we have the vector functions x1, x2, and x3 are solutions to a system, to the homogeneous case. Determine whether they form a fundamental solution set. If they do, find a fundamental matrix for the system and give a general solution. All right, example 4. So we have these 3 vector functions, x1, x2, and x3, and they are solutions to system x prime minus x equal to 0. So equal to 0 meaning that's a homogeneous case. All right, so let's pause here, go back to our notes, and look at how we can come up with a general solution. All right, so 9.4.1 approach to solving normal system. Since we are looking at a homogeneous case equal to 0, we're looking at the first one. All right, so first thing, find a fundamental solution set x1 to xn. So that's actually given to us. That consists of unlinearly independent solution to the homogeneous system. All right, so first thing we need to check is that the three vector functions that we're given, are they linearly independent? Right, let's check that first. All right, so to check if these three are linearly independent, there are many ways, right? You can use the Wronskian, or you can use a trial and error. Now, since it's we have three vector functions and each one of them has three entries, all right, let's try the Wronskian and see if that will work. All right, so Wronskian is going to be e to the t, e to the t, e to the t, sine t, cosine t, negative sine t. All right. All right. So Wronskian is going to be the determinant of this, right? Go ahead and you can pause the video if you want to try yourself, or I'm going to just write out what the determinant is in a second. Okay. So I found that the Wronskian is 2 times e to the t. Now e to the t is never 0, right? So the Wronskian is never 0. That means they are linearly independent. Okay, so in this case, Wronskian is very useful because it happens to be linearly independent, which I would say in a lot of cases they are going to be linearly independent. Okay, all right, so let's see what's next. Now that we have checked they are linearly independent. All right, so part B, once we have shown that they are linearly independent solutions, form the linear combination x is equal to capital X times c, or the linear combination c1 up to cn for the coefficient and x1, xn, where c is any constant vector, right, is the fundamental matrix to obtain the general solution. All right, so basically put them in a linear combination form. All right, so here we go. We know that they're linearly independent, right? So our solution x is going to be c1x1 plus c2x2 plus c3x3, right? Whereas c1, c2, and c3, there are some constant. And in order to find out what c1, c2, and c3s are, remember we will actually need some initial condition. Right. So since in this case we are not given an initial condition, all we need to do is just find the general solution, right? And let me just write out some different ways of representing the general solution. Right. So we can write that as C1, and then actually writing out the matrix. Not the matrix, the vector function. Right. C2. Okay, like this, right? Or there's another way you can represent this, represent the general solution X using a matrix, right? So we're gonna put a matrix like this, and then each of the column are your x1, x2, and x3, and multiply by the constants c1, c2, and c3, like that. Okay, so there's another way of representing your solution. Right? Yeah, that's it. So this example is for the homogeneous case, and for the non-homogeneous case, all you need to do is take this, right? That's the homogeneous solution, and add xp at the particular solution for a non-homogeneous case, right? And that's the only difference. So let's take a look at this example again, right? So we're given three solutions, and we want to make sure that they are linearly independent, right? So you check that using a Wronskian or some other method, right? If they are linearly independent, then just go ahead and put them in the form of a linear combination using some constant C1, C2, and C3. And of course, again, we need initial value to figure out what those are. But in this case, we're not going to worry about that. And for non-homogeneous case, you just need to add the extra particular solutions to the homogeneous case. Okay, and that will be all for 9.4. Thank you guys very much. Have a good day.